Good morning, everyone. I am Dipanji from BSc Chemistry on a third year. Sample preparation. For sample preparation, 20 mg of pure crystalline compound is dissolved in 0.5 ml of solvent in a clean NMR tube in presence of internal standard. Position of signal. Chemical shift. The difference in the resonance frequency of a given proton and the resonance frequency of a methyl proton of TMS under experimental condition is called chemical shift. Chemical shift is equal to V mu s minus mu tms by operating frequency into 10 h per 6 ppm. The chemical shift is measured in two scales, delta scale, tau scale. It ranges from 0 to 10 for PMR, tau scale, tau is equal to 10 ppm. The NMR spectra, the graph which is a plot between intensity of NMR signal and magnetic field in reference to TMS is called NMR spectra. Electronegativity. Carbon is more electronegative than silicon. Electron density around CH3 proton is very high. Sample preparation. For sample preparation, 20 mg of pure crystalline compound is dissolved in 0.5 ml solvent in a clean NMR tube in the presence of internal standard. NMR solvent for sample preparation. For PMR spectra, the solvent should be inexpensive, have low boiling point, non-polar, chemically inert, aprotic, internal standard. The tetramethyl silane is generally used as internal standard to determine the position of signal for H1C13 Si20 nuclei in NMR spectra. Magnetically isotropic solvent. The solvent generally used are CdCl3, DMSO, D6CH3OH, D4, D2O, C6, D6. It contains 12 magnetically equivalent protons, thus give a single sharp line. Its resonance position is far away from the resonance position of protons in most organic compounds. So the resonance position of TMS is arbitrarily assigned as 0. Chemically inert, miscible with large range of solvents, highly volatile and thus can be removed easily during the recovery of sample compound. It does not involve any intermolecular association with the sample. Induced magnetic field. The magnetic field produced by electron on spinning in presence of applied magnetic field is called induced or secondary magnetic field. Why hydrogen nuclei in all compound do not resonate at same value of applied magnetic field? The chemical of hydrogen in all nuclei in all compounds is not same. They have different electron density around them. So hydrogen nuclei in all compound do not resonate at same value of applied magnetic field. Representation of induced magnetic field produced by sigma electron. Representation of induced magnetic field produced by pi electron. Representation of applied magnetic field produced by magnets. Organic compound. If protons are surrounded by only sigma electrons, then ES electron spin complex on their axis produce induced magnetic field, which always opposes applied magnetic field. Thus, the effective magnetic field experienced by the proton is always less than applied magnetic field. So, proton will always resonate at high value of applied magnetic field. CH3, thenon protons surround with same electron density, induced magnetic field and more applied magnetic field. If protons are surrounded by pi electron, then pi electron spin on their axis produces induced magnetic field, which may oppose or reinforce applied magnetic field depending upon the orientation of molecule in applied magnetic field, and thus effective magnetic field experienced by the proton may be less or more than applied magnetic field. So proton may resonate at high value or low value of applied magnetic field. Example, in external magnetic field, the ethene molecule assume horizontal orientation. Thus, the induced magnetic field produced by circulation of pi electron has reinforced applied magnetic field in the region of proton. Protons are de-shielded, so the ethylene protons will resonate at lower value of applied magnetic field. Example, in external magnetic field, the ethine molecule assume vertical orientation and thus the induced magnetic field produced by the circulation of pi ES opposes the applied magnetic field in the region of proton. Protons are shielded, so the ethine protons will resonate at higher value of applied magnetic field. Shielding and de-shielding in compounds having conjugated pi bonds in aromatic ring. The conjugated pi electrons on circulation produces cylindrically secondary field called ring currents which oppose the applied magnetic field in the center of molecule and reinforce the applied magnetic field at the periphery of ring. Aromatic protons present at the periphery of ring get de-shielded. So the aromatic proton resonates at lower value of applied magnetic field. Anisotropic effect. The effect when one part of the molecule observe less applied magnetic field and some other part observe more applied magnetic field is called anisotropic effect. Chemical shift values for various type of hydrogen RCH3, CH2, CH 0.0 to 1.7, RnH2, NHR 0.5 to 5.0, ROH 0.5 to 5.5, ArCH3 CH2 and R2 CH2 SOIO CH2S C triple bond CH 1.7 to 3.0, CH3OR CH3O AR 3.3 to 3.7, RCOO CH3 ArCOO CH3 3.6 to 3.9, AROH 4.0 to 7, C double bond CH 4.5 to 7, CONHR 5.0 to 8.0, AR 7.0 to 8.0, RCHO 9.5 to 10, RCOH 10.5 to 12, C double bond COH 15 to 17. Chemical shift mu as hertz, mu TMS hertz by operating frequency in megahertz into percentage per 6 ppm. Effect of inductive effect and resonance on alpha beta protons in unsaturated ethers. Substituted vinyl ethers. The electron density around alpha proton decreased due to the negative inductive effect of O atom. Alpha proton get deshielded, so alpha hydrogen atom will resonate at lower value of applied magnetic field. But the electron density around beta proton increases due to the resonance. Beta proton get shielded due to resonance, and the beta hydrogen atom will resonate at higher value of applied magnetic field. How can you differentiate between paraxylene and mazitylene using NMR spectra? In paraxylene, there are two types of proton, proton A, B. All three CH3 proton are equivalent to give one signal. Proton B, all the benzene proton are equivalent to give one signal. Difference. In paraxylene, the relative intensity of two types of proton, CH3 proton and proton B, benzene proton, is 6:4 or 3:2. While in mazitylene, there are two types of proton. Proton A, all three CH3 proton are equivalent to 1. Proton, all benzene proton are equivalent to 1. Difference in mazitylene, the relative intensity of two types of proton A and proton B is 9:3 or 3:1. How can you differentiate between primary, secondary, and tertiary alcohol using NMR? The OH proton in primary alcohol on splitting gives triplet due to the presence of two neighboring hydrogen atoms, while OH proton secondary alcohol on doublet due to the presence of two neighboring hydrogen atoms. And the OH proton in secondary alcohol gives splitting singlet due to the presence of one neighboring hydrogen atom. Why is splitting observed in 2-methylpropene but not in neopentyl chloride? In 2-methylpropene, the CH3 proton HA and HB are closer to each other due to the shorter sp2 hybridized carbon-carbon bond. Thus, CH3 proton and HB proton can couple with each other, which result in splitting of signals into peak. In neopentyl chloride, CH3 protons are far away to each other due to the longer sp3 hybridized carbon-carbon bond, and the CH3 protons, HA and CH2 protons cannot couple with each other. No splitting of the signal occurs. Determination of equivalent homotopic proton in substituted benzene. Always draw bonds all hydrogen atom with ring carbon atom. Ortho, para, then meta. Not a substituent is neither strongly electron releasing nor a strongly electron withdrawing group. Then all the benzene proton give rise to a single resonance despite the proton HA, HB, HC are not chemical equivalent. Reason the small chemical shape difference are same but eliminated by the presence of ring current. Determination of equivalent homotopic protons in cycloalkene. Always draw all bonds of hydrogen atom with ring C. Determination of homotopic protons in alkene. Always draw all bonds with doubly bonded carbon atom. All proton are equivalent cyclopropane. 1-methyl cyclopropane, 4 type of protons. 2-methyl butene, cis-butene, trans-butene. Effect of changing solvent. The value of chemical shift always changes with the change of solvent. If the solvent interacts with given substance to form complex, it will affect the deshielding of hydrogen atom of given substance, thus can affect the resonance frequency or chemical shift. Van der Waals deshielding. The decrease in electron density and sterically hindered hydrogen atom due to repulsion of electron cloud of hydrogen atom by electron cloud of bulky groups is called van der Waals deshielding. Structure on proton A has no effect of proton B, but in structure 2, proton A is affected by CH3 group. The electron density increase of deshielding around the sterically hindered hydrogen atom decreases due to the repulsion of electron cloud of H atom by electron cloud of bulky sterically hindered CH3. Effect of dilution or change of temperature on intramolecular hydrogen bonding. With dilution, the extent of intramolecular hydrogen bonding remains same, so hydrogen atom will resonate at the same value of applied magnetic field. With dilution or increase of temperature, the extent of intramolecular hydrogen bonding remains same. So hydrogen atom will resonate at same value of applied magnetic field at the same value of chemical shift. Van der Waals bond orthonitrophenol and orthonitrophenol. At high temperature, vapor phase and dilute form electron density around hydrogen atom remains same. Effect of dilution or change of temperature on intermolecular hydrogen bonding. With dilution or increase of temperature, the extent of intermolecular hydrogen bonding decrease and thus there will be maximum electron density around hydrogen atom, more shielding of protons. So hydrogen atom will resonate at higher value of applied magnetic field at low temperature and concentrated from the electron density around hydrogen atom is minimum. At high temperature, vapor phase and dilute form electron density around hydrogen atom is maximum. The strength of hydrogen bonding depends upon concentration and temperature. In concentrated solution, the molecules are more closer to each other, so more will be the magnitude of hydrogen bonding, and thus the hydrogen bonding involves electron cloud transfer from hydrogen atom to neighboring electronegative atom, so de-shielding of hydrogen atom takes place. Hence, the hydrogen atom will resonate at lower value of applied magnetic field at higher value of del. Electron density around hydrogen atom decreases. Effect of resonance on ortho, meta, and para protons in substituted benzene. In polysubstituted benzene in compound, the value of chemical shift increment is added in the basic value of monosubstituted benzene ring. The de-shielding proton ortho, para, meta. CH3 0.5, 0.1, 0.1. COOH. The value of chemical shift increment is added in the basic value of monosubstituted benzene ring. De-shielding of protons ortho, para, meta. Substituents shift in ortho, meta, para proton position of benzene proton. CH3 0.15, 0.1, 0.1. COOH 0.8, 0.15, 0.2. COOCH3 0.8, 0.15, 0.2. CN 0.3, 0.3, 0.3. CONH2 0.5, 0.2, 0.2. COR 0.6, 0.3, 0.3. NH2 0.8, 0.15, 0.4. CHO 0.7, 0.2, 0.4. OH 0.4, 0.4, 0.4. NO2 1.0, 0.3, 0.4. OCH3 0.2, 0.2, 0.2. OCOCH3 0.4, 0.1, 0.4. Effect of resonance on ortho, meta, and para position in substituted benzene. In monosubstituted benzene ring compounds, ortho and para hydrogen atoms will resonate at lower value of applied magnetic field than meta protons. If substituent is -R effect group, then the electron density around ortho and para proton decreases. Ortho and para proton get de-shielded. The de-shielding of protons ortho, para, meta. Substituent shift in ortho, para, meta position of benzene protons. Del is equal to 7.27. CH3 key value is 0.15, 0.1, 0.1. COOH 0.8, 0.15, 0.2. COOCH3 0.8, 0.15, 0.2. CN 0.3, 0.3, 0.3. CONH2 0.5, 0.2, 0.2. COR 0.6, 0.3, 0.3. NH2 0.8, 0.15, 0.4. CHO 0.7, 0.2, 0.4. OH 0.4, 0.4, 0.4. NO2 1.0, 0.3, 0.4. OCH3 0.2, 0.2, 0.2. OCOCH3 0.4, 0.1, 0.4. Low magnetic field, less shielded proton surrounded by less electron density, proton surrounded by more electron density, more shielded, high magnetic field. Effect of resonance on ortho, meta, and para position in substituted benzene. In monosubstituted benzene ring, ortho and para hydrogen atom will resonate at higher value of applied magnetic field than meta proton. If substituent is +R effect, then the electron density around ortho and para proton increases. Ortho and para proton get shielded. The shielding of proton is ortho, para, meta. Substituents. Serial number substituent shift in ortho, meta, para position of benzene protons. Del is equal to 7.27. CH3 0.15, 0.1, 0.1. COOH 0.8, 0.15, 0.2. COOCH3 0.8, 0.15, 0.2. CN 0.3, 0.3, 0.3. CONH2 0.5, 0.2, 0.2. COR 0.6, 0.3, 0.3. NH2 0.8, 0.15, 0.4. CHO 0.7, 0.2, 0.4. OH 0.4, 0.4, 0.4. NO2 1.0, 0.3, 0.4. Determine the molecular structure of given compound having molecular formula C9H12 on the basis of the following NMR data. Del is equal to 7.1, del is equal to 2.2, del is equal to 1.5, del is equal to 0.9. The HDI of the given compound having molecular formula C9H12 is 2C plus 2 minus x by 2. 20 minus 12 by 2 is equal to 4. The del is equal to 0.7.28. 5H indicates that the 4HDI is due to the 1 benzene ring and 3 double bond. The presence of 5H indicates that the benzene ring is mono-substituted. C9H12 dot C5H5 C3H7 on benzene. So the possible arrangement of C3H7 is given here. Determine the molecular structure of compound having molecular formula C5H8 on the basis of the following NMR data. Del is equal to 8.8 T3H, del is equal to 8.2S 3H, del is equal to 7.8 Q2H. The HDI of a given compound having molecular formula C5H8 is 2C plus 2 minus x by 2, 12 minus 8 by 2 is equal to 2. The molecular formula C5H8 indicates that del will have greater value than 7.0 is not of benzene ring. The 2 HDI is due to the small ring and 2 double bond or 1 double bond is small ring or 1 triple bond. So the possible arrangement of carbon skeleton with del is equal to 8.8 T3H, del is equal to 8.2 del S3H, del is equal to 7.9 Q2H. So the correct answer structure is 1. Determine the molecular structure of given compound having molecular formula C10H14 on the basis of following NMR data. Del is equal to 7.8 5H 0.88 9H. HDI of a given compound using molecular formula C10H14 is 2C plus 2 minus x by 2. 22 minus 14 by 2 is equal to 4. Del is equal to 7.28 indicates that 4HDI is due to the 1 benzene ring, 3 double bond. The presence of 5H indicates that the benzene ring is mono-substituted. So the possible arrangement of the C4H9 is follows. Determine the molecular structure of given compound having the molecular formula C9H11Br on the basis of following NMR. Del is equal to 7.22, del is equal to 3.38, del is equal to 2.75, del is equal to 2.15. The HDI of the given compound having molecular formula C9H11Br is 2C plus 2 minus x by 2, 20 minus 11 minus 1 by 2 is equal to 4. The del is 7.22 indicates that the 4HDI is due to the 1 benzene ring, 3 double bond. The presence of 5H indicates that the benzene ring is mono-substituted. So the possible arrangement of C3H6Br are given below. Del is equal to 3.38, B del is equal to 2.75, del is equal to 2.15 indicates that question. Determine the molecular structure of carbon compound having molecular formula C10H12O on the basis of NMR data. Del is equal to 7.22S5H, del is equal to 3.59S2H, del is equal to 2.7577Q2H, del is equal to 0.97T3H. The HDI of a given carbonyl compound having molecular formula C10H12O is 2C plus 2 by 2 minus x, 22 minus 12 by 2 5. The del is equal to 7.22 indicates that the 4HDI is due to the 1 benzene ring, 3 double bond. The presence of 5H indicates that the benzene ring is mono-substituted. The 1 HDI should be due to the carbon double bond O double bond. So the possible arrangement of substituent C4H7O are PMR spectra of para-nitrotoluene. Number of type of proton 3 ABC. Number of signal 3, intensity of signal A ratio, B ratio is 3 ratio, 2 ratio 2, position of signal 2.5, 7.3, 8.0, CH3 singlet due to no neighboring proton, PB, PHH multiplied due to the remaining PH protons, PHH multiplied due to remaining PH proton and 8. Intensity of lines in a multiple 1 ratio multiplied. PMR spectra of para-anisidine. Number of type of proton 4. Number of signal 4, intensity A, B ratio, A ratio, B ratio, C ratio, D, 2 ratio, 3 ratio, 2 ratio 2, position of signal, del is equal to 3.4, del B is equal to 3.75, del C is equal to 6.55 to 6.65, del D is equal to 6.70 to 6.75. NH2 singlet due to no neighboring proton, CH3 singlet due to no neighboring proton, phenyl H multiplied due to the remaining phenyl proton, PHH multiplied due to the remaining PH proton. Intensity of lines in a multiple 1 ratio multiplied. PMR spectra of acetophenone. The number of type of proton 2AB, number of signal 2, intensity of signal A ratio B 3 ratio 5, position of signal 2.25 Del B 7.41 to 7.81. Singlet due to no-neighboring proton. Multiplet due to remaining pH proton. PHH multiplet due to remaining pH proton. PMR spectra of benzaldehyde. Number of type of proton 2AB, number of signal 2, intensity of signal A ratio B 1 ratio 5, position of signal del A 9.8, signal 7.4 to 7.72, multiplicity of signal CHO singlet due to non-neighboring proton, PHH multiplied due to no remaining pH proton, pH multiplied due to remaining pH proton, intensity of lines in a multiplet 1 ratio multiplet. PMR spectra of toluene. Number of type of proton 2A, B, C. Number of signal 2A. Intensity of signal A ratio B 5 ratio 3. Position of signal 7.75 del A 2.232 del B. Multiplicity of signal phenyl as signal due to effect of ring current multiplied at 300 megahertz. Intensity of lines in a multiplet 1 ratio CSC singlet due to no neighboring proton. PMR spectra of ethyl acetate. Number of types of proton 3A, B and C. Number of signal 3. Intensity of signal A ratio B ratio 3, 2 ratio 3 ratio 3. Position of signal del A is equal to 4.15, del B is equal to 2.0 and del C is equal to 1.25. Multiplicity of signal quadruplet due to 3 neighboring protons. Singlet due to no neighboring proton. Triplet due to 2 neighboring protons. PMR of acetaldehyde. Number of type of proton 2A and B. Number of signal 2. Intensity of signal A ratio B 1 ratio 3. Position of signal del A 9.68, del B 2.15. Multiplicity of signal CHO quadruplet due to 3 neighboring proton. CH3 doublet due to 1 neighboring proton. 1 ratio 3 ratio 3 ratio 1. 1 ratio 1. Intensity of lines in a multiplet. PMR spectra of ethanol. Number of type of proton 3A, B and C. Number of signal 3. Intensity of signal A ratio B ratio C 1 ratio 2 ratio 3. Position of signal del A is equal to 5.37, del B is equal to 3.62, del C is equal to 1.17. Multiplicity of signal OH singlet due to non-neighboring proton, CH quadruplet due to 3 neighboring proton, triplet due to 2 neighboring proton. Intensity of lines and a multiplet 1 ratio 3 ratio 3 ratio 1, 1 ratio 2 ratio 1. PMR spectra of anhydrous ethanol. Number of type of proton 3A, B and C. Number of signal 3. Intensity of signal A ratio B ratio 3, C 1 ratio 2 ratio 3. Position of signal del A is equal to 5.28, del B is equal to 3.62, del C is equal to 1.18. Multiplicity of signal OH triplet due to 2 neighboring proton, multiplet lines due to 2 kinds of 4, 3 plus 1 neighboring proton, triplet due to 2 neighboring proton. Intensity of lines in a multiplet 1 ratio 2 ratio 1 as per Pascal triangle. PMR spectra of 112 tribromoethane. 60 megahertz spectra no splitting, 300 megahertz spectra splitting of signal. Number of type of proton 2 A and B. Number of signal 2. Intensity of signal A ratio B 1 ratio 2. Position of signal 5.7 del A 4.2 del B. Multiplicity of signal CH triplet due to 2 neighboring protons, doublet due to 1 neighboring proton. PMR spectra 1 dibromoethane. Number of type of proton 2A and B. Number of signal 2. Intensity of signal A ratio B 1 ratio 3. Position of signal del A 5.85, del B 2.5. Multiplicity of signal quadruplet due to 4 neighboring proton, doublet due to 1 neighboring proton CH3. Intensity of lines in a multiplet 1 ratio 3 ratio 3 ratio 1 1 ratio 1. PMR spectra of isopropyl bromide. Number of type of proton 2A and B. Number of signal 2. Intensity of signal A ratio B 1 ratio 6. Position of signal del is equal to 4.3. Del B is equal to 1.75. Multiplicity of signal septet due to 6 neighboring protons. CH3 doublet due to 1 neighboring proton. Intensity of lines in a multiplet 1 ratio 6, 15 ratio 20, 15 ratio 6 ratio 1, 1 ratio 1. PMR spectra of non-propyl bromide. Number of type of proton 3 A, B and C. Number of signal 3. Intensity of signal A ratio B ratio C 2 ratio 2 ratio 3. Position of signal del A is equal to 3.45, del B is equal to 1.95, del C is equal to 1.1. Multiplicity of signal triplet due to 2 neighboring protons, multiplet due to 5 neighboring proton hexadet, triplet due to 2 neighboring proton. Intensity of lines in a multiplet 1 ratio 2 ratio 1, 1 ratio 5 ratio 10 ratio 10 ratio 5 ratio 1, 1 ratio 2 ratio 1. PMR spectra of ethyl bromide. Number of type of proton 2A and B. Number of signal 2. Intensity of signal A ratio B 2 ratio 3, position of signal del is equal to 3.4, del B is equal to 1.7. Multiplicity of signal quadruplet due to 3 equivalent proton of neighboring methyl group, triplet due to 2 equivalent proton of neighboring methyl group. 1 ratio 3 ratio 3 ratio 1, 1 ratio 2 ratio 1. Intensity of lines in a multiplet. Thank you.